It is great to have you with us this afternoon. I have planned a really exciting session for you this afternoon, and I need your participation, and I need for you to be listening throughout the presentation. And please ask questions if if there is an occasion, I will definitely address all of your concerns, all your questions uh, as they come up. And if there is any issue that I don't resolve for you by the end of this session, feel free to send me an email, and I will communicate with you. Anyway, today, as I said, it's an exciting presentation about strength of materials. What we will cover will be following exactly the topics that are identified in the NCEES documents under strength of materials or mechanics of materials. And as we go along, I will tell you that the title or the topic, the exact term that they use in their document. Anyway, let's get this started, and we will begin by the idea of stress versus strain. And all of you have seen this material on during your education in a course probably called Mechanics of Solids or Strength of Materials. And let's take a look at the concept of stress versus strain. And this is something that you're going to hear me talk about quite a bit throughout the session, and you really need to have a good understanding of these concepts. Stress. Simply, we can express stress as the force divided by the area. Remember, we use the Greek letter sigma. Sigma is what we use to designate stress. And in this particular case, we are talking about normal stress. Normal, not in the sense that it is ordinary, but it is, we call it normal because it is produced by a force that is perpendicular or normal to the area. And in a case like that, we simply take the force, in this case, let's call it P, divided by the cross-sectional area over which it's acting. All right? So that is the concept of stress. With stress goes strain, and I need for you to really pay very close attention, because a lot of people make a very common mistake when they think about strain. Whenever stress happens, it causes certain type of strain. In this case, since the stress is normal stress, sigma, it causes normal strain. And please pay attention, the equation down below. This is the equation you use to find the corresponding strain. And we use the Greek letter epsilon to represent that. So epsilon is equal to delta L over L. Now, please pay very close attention to what is in the numerator. The numerator is delta L. Delta L is simply change in length. Okay? It's not length, it's change in length divided by the original length. All right? So when normal stress, let's say it's in tension, it causes extension of a member. The amount that it is extended, that would be the change in length, or delta L, and you take that divided by the original length, and that would give you strain. The common mistake is that some people, when they talk about strain, they just think it is change in length. It is not. Strain is change in length, always divided by the original length. Please make sure that you remember that. Now, a structural engineer or a materials engineer, they can look at a curve that we call stress strain for a given material, and they can, by looking at this stress strain curve, they can estimate the behavior of that particular material under force. And what I need for you to understand is the shape of the stress-strain curve here. This is for a typical ductile material, and there are certain points along this stress-strain curve that are important, and for the test you need to know the definitions of those points. So let's begin by the first point that I want you to understand. It is called proportional limit. All right, proportional limit. What I want you to do is be able to approximately locate and decide where along the curve this point would be, the point that's called proportional limit. And then also I want you to be able to come up with a definition. Again, they will not ask you to define it. They will give you 4 choices, and they say, well, which of these definitions would be the proportional limit? All right? Okay, so proportional limit simply is the point on the curve below which the stress and strain are proportional. In other words, all the points below the proportional limit on this curve, they are proportional. The x and y between the point 0, 0 and proportional limit, the x and y are proportional, meaning that part of the curve is linear. All right? So that's how we would define proportional limit. Let's go to the next point that's significant. And this is elastic limit. This point is called elastic limit, and the way we define this is that below the elastic limit, the material behaves elastically or in an elastic manner. However, as the stress increases, in other words, the stress is higher than the elastic limit, then the material behaves in an inelastic or plastic manner. You may ask, what does that mean that a material behaves in an elastic manner? I will tell you very quickly. Let's assume that we have some type of an object. It could be a structural element. And if we place certain amount of load on it, this force causes some type of deformation. Now, if you remove the load and the material goes back to its original shape, that is called elastic behavior. However, if you place a load on the material, it causes some deformations, let's say some change of shape, and then you remove the load, but the material does not go back to its original shape. In other words, some of the displacement remains. That is called inelastic or plastic behavior. Now, the third important point that I want to share with you is called yield point. Now, approximately, it is for a ductile material, the location of the yield point is approximately where this double kink occurs. And I think you could, you know what I'm talking about, the double kink in this area. All right? And that actually, yield point is where the material yields. You may ask, what does that mean when you say the material yields? In order to answer that question, I would like to go to the next slide. But before I do that, Mary, I see your question here. I will ask. I will answer that when I get a chance. And Paul has a question. Paul is asking, would you describe the difference between the elastic limit and the proportional limit? the proportional limit, as I said, below that point, the stress strain curve is linear. X and Y are dependent on each other. They're proportional to each other. The elastic limit is somewhat higher than the proportional limit. So they are not exact same point. However, from a practical point of view, those of you who are structural engineers or material engineers, you know from a practical point of view, it's very difficult to distinguish between the 2 points. There are a lot of cases where we take the same value as the elastic limit or the proportional limit. But I got to tell you guys, the exam you're about to take is not a practical exam. It's highly theoretical. So you need to know that there is a difference between the two. I hope that answered your concern, Paul. Now, as I told you, I want to use this slide number 7, to demonstrate to you what yield behavior is. All right? Now, here's what I want you to please imagine. Remember I told you about this double kink? Well, what if I come along and rather than showing the double kink, I approximate the behavior? We engineers, we like to approximate and simplify things. So can you imagine that we eliminate the double kink, the kink on the left and the right, and we can assume if those areas are the same, so they cancel each other out, but concentrate on that red line. It's a horizontal line. In fact, those of you who are familiar with design of steel structures, you know AISC. That stands for American Institute of Steel Construction. AISC, when they plot the stress strain curve for certain grades of steel, in fact, that's what they do. They don't show the double kink. That area of double kink, they just show the straight line like that red line that I'm showing. All right? Now, I need your help. If we have a graph, and this is a graph, it's just a relationship between the X and Y. Now, X here, please pay attention, X is strain, Y is stress. So this really just shows, this graph shows the relationship between stress and strain. Tell me, mathematically, if a portion of that curve is a horizontal line, what is that telling us about the relationship between X and Y? And if you can answer that question, then you will have a good understanding of actually what happens when a material yields. So who can tell me, what, based on what I've said, what do you think, what does it mean when the curve, the portion of the curve is just a straight line? Matthew says strain increases without additional stress. Helen says it gets longer with no load added. Yes. Mary, strain continues even when stress stays the same. Absolutely. All of these, and many of you, Arash, Ryan, Laura, you're answering questions. This is basically what happens. All right. This is what happens, guys. When the horizontal line says, look, the Y value stays the same. Think about it. That horizontal line has the same Y value no matter where you are. However, at that same Y value, X increases. So many of you, all of you actually, that answered it, you answered it correctly. So guys, this is the answer. What happens at yield is that stress remains constant. However, strain keeps on increasing. That's what we mean by yielding. In terms of force, you can think about it this way. The force stays constant, but the material keeps on deforming when it reaches yield. All right, let's move on. The next point of interest